Welcome to presentation 28. Today's presentation we're going to talk about the Secure Digital Card High Capacity, SDHC. This is going to be one of three presentations talking about the SDHC. As usual, we're going to start by looking at our architecture. So the SDHC belongs to our layer 3, and we're going to use certain functions from layer 2, which is going to be the UART, the SPI framework, some I/O ports, and also interrupts. So let's look at the agenda. So for today, first I'm going to give you a description of the DHC. I'm going to give you descriptions, I said, sorry. Next, we're going to talk about the data sheet. I'm going to give you a high-level description of the data sheet, or I should say presentation to the data sheet. Next, we're going to talk about the functionality and sample programs. And finally, we're going to go through the summary. So let's start with the description. So this is what the SDHC looks like, and this is, we could say this is the card reader, and this is the SD card that fits in. And here you can see this SD card ready to go, inserted into the card reader. Now the interface to the card reader is going to be what it has, I should say. It's has a pin for a ground, 3 volts, 5 volts. Then it has a chip select, MOSI, clock, MISO, and ground. So it has all the facilities, so we can hook up our SPI, and also we can run it with 3 volts or 5 volts. We see the one it works. So let's look at let's start by give you an introduction to the specification. As usual, our first stop is the specification to figure out how do we go about programming the SDHC. So this is the specification we use for starters, and which is the SD specification, part 1, physical layer, simplify specification version 9.10, December 1, 2023. This is by the Technical Committee, SD Card Association. So what I'm going to do is I'm just going to highlight some of the sections that I consider most relevant. So let me go to the index and show you where this section is. That's going to be in section 7. As I go, you're going to see how much information is here. It's incredible. So here we are in section 7, which is SPI mode, because it's very relevant, because we're going to communicate with our SDHC through the through the SPI. So in this section, we're going to find some fairly important information that I'm going to just highlight. So for example, we're going to have SD card state diagram, which is really important to see how things work. Another good information is going to be the initialization flow. Next, we'll have how data is read, data is written, some of the erase and write protect managements, and so forth and so on. So you kind of get a flavor, or this is a good place to start without being overwhelmed by the amount of information that there is in this document and in many other documents. So with this, you kind of get an idea about the place where to stop to get the information. And let's continue with the presentation. Okay, so let's continue. And first thing I'm going to do is I'm going to show you what a command looks like. So when we communicate with the SDHC, the communication is going to be accomplished by sending commands to the SDHC. So, and each command, of course, is going to be through the SPI. So a command are issued over the SPI interface in 6-byte structure. The last byte contains the CRC with the final stop bit equal to 1. So basically what we do is if we want to send a command, we have to send 6 bytes. The first byte has the command number. Then we're going to have 4 bytes of arguments, and next we're going to have the CRC. The commands that we're going to use are basically commands 0, 8, 12, 16, 17, 18, 24, 41, 55, 58, and 59. Now the definition of those commands, of course, they are all contained on the spec, but I'm just going to give you also a good presentation about the commands so you can get an idea how to use them. So let's start with the agenda dealing with how we're going to go about learning about the commands. So first we're going to have I'm going to give you information about how to initialize the SDHC, and so that's going to be done by showing you data flow. Next, data flow is going to show some of the commands that we use, and so I'm going to give you also a definition of each of those commands. Next, I'll give you a sample program. That's item 1. Item 2, we're going to learn how to read a single block from a sector. So first, we learn how to initialize the sector. And I'm breaking this in parts and having a sample program because otherwise we end up with too many lines of code and very difficult to understand. So next, we're going to learn how to read a single sector. So to learn how to read a single sector, we're going to go again through the data flow. Then we're going to learn about the commands required to do a single read, which is going to be command 1617. Next, we'll do a sample program on how to read a single block. Next, we'll do how to read multiple sectors. Again, we'll start with the data flow, the commands required, and a sample program. And the final item of this presentation is going to be how to write data into a sector. So we'll do the data flow and finally a sample program. So let's get going with the initialization. So every time we want to use the SDHC, we're going to be required to initialize the card. So on the initialization, I'm going to present a data flow of the initialization. Then the commands, I'm going to explain each of the commands needed for the initialization. We'll go through a sample and we'll go through a sample program. So let's get started with the initialization. This flow shows what we need to do to initialize the SDHC. So the way we do that is by sending a series of commands and verifying that each of the command is being processed successfully by the SDHC. So the commands we need to send is command 0, command 8, command 59, command 58, command 55, and then command 41. Once we get to command 41, to verify that everything got initialized correctly, we request the output from command we expect to get a reply from command 41 to be 00. If we don't get that, then we send command 55 again, followed by command 41, and we review the reply from command 41, and eventually it's going to be 0, which we declare that the SDHC has been programmed, or we'll get, in the other cases, we would get a timeout, and that's we're done. So let's look at the code, how we send command, how we initialize, I should say. So we have a routine that's called init SDHC, and one of the things that we have to do, required by the hardware, is to do a 80 clocks that we idle, where we send a message 0FF. So once we accomplish that, then we're ready to start sending out our commands. So that 80 clock cycle would be like to wake up the SDHC. So then we go ahead and send the command 08, 59, 58, 55 and 41. So these are the routines that are going to take care to transmit the command and also verify that the command was successfully processed by the SDHC. Next, after sending all those commands, then what we do is, like I noted, we send command 55 again, and then command 41, and we check for the output from command 41, and when the output is 0, then we can then we know that the SDHC has been initialized. So now let's go to see what each command looks like. So let's start with command 0. So in this picture, I show what the command is going to look like. So basically, it is 6 bytes that we send, and we're going to get 1 byte of reply after we transmitted this. Now, the format of command 0 is very specific. It's going to be, we send a hex 40, which is the command number, followed by all 0. So basically, all the arguments are 0 for this that we transmit for this particular command, and then we follow by a 95. This is exactly what we need to send. Next, we have, let's look at the actual code that accomplishes this. So we have the routine, which we call transmit command 0. And the first thing we do is we load create an array that is going to contain, I should say, the command itself. So here we have command CMD array, which has the parameters 40, 00095, which is exactly command 0 that we have to transmit. So one of the things that I forget to mention, the transmit command 0 is going to do 2 things. One of the things it's going to do is going to send the command to the SDHC, but also it's going to send a message to a laptop through a UART serial connection, so we know by looking at a laptop in real time what's going on. So this is this for loop, I should say, sends the command to the SDHC. So here, and to the laptop. So here we have serial UIN16, which is sending the command to the laptop, so the UART, and this is sending the command to the SDHC through the SPI. So with 6 parameters, we go 6 times. Now, after we've completed sending the command, the next step we have to do is verify that the command has been successfully processed. So we do like this as follows. What we're going to do is we're going to ask the SDHC 8 times to get it sends dummy message, so we get a response, which is going to be the status. And we're going to give 8 opportunities to get the the status equal to a 0 on bit 7, which is the 80 hex. And once we do that, then we're going to declare success. If we don't ever get this to be true, which is the bit 7 equal to 0, then we are not going to report anything, which means that we had a failure. So here we go, the 8 times, send a dummy message, SPI transfer 0xx, and then we read the reply, which is the status. And as soon as we get the status equal to 0 for bit 7, then we can say that the command had been processed successfully. So that's then last thing we do here, we select the HDAC SPI channel, and that concludes command 0. The next command we have to look for the initialization is command 8. Command 8, we're going to send these 6 bytes, and we're going to get a 5 bytes in response. So what we send, basically the command number is going to be 48, and then the arguments are going to be 0, 0, 1, AA, and then the checksums to be 87. So what we would expect to get back would be the R1 response, which should be 0. Then we want to get a word that says that the voltage was within range, and finally we wanted to echo back a particular parameter, which in this case is AA in byte 5. So basically what I'm saying here is that byte 4 is going to be that the voltage is within range, which is a 0, 1, and then byte 5 is going to be an AA, which is the pattern that we sent. So let's look at the code. So again, we have an array that has exactly the parameters that we need to transmit for command 8. So then we chip select the SDHC, and now I sent here a dummy SPI transceiver with 0FF, and that I have to do because that seems to work better if we do that. It's kind of like a wake up message. Next, I send the 6 parameters, 6 parameters to the SDHC and also to the laptop. Once we've done that, now what we need to do is we need to start getting status back from the SDHC. Now there are a lot of parameters that we're going to have to check. So we're going to have to check bit 1, and we're going to have to check bit 4 for the voltage accepted, and bit 5 for the echo response. So what we do is first we go 8 times around the loop, and so we set the command. Then we go 8 times and fill up and put all the data into an array. So we have all the replies from the SDHC, and what we have to do is get those reply and ensure that we got the correct response for successful transmission, and also for correct pattern and for voltage within range. So the first thing we do is we test for the 08, which what it's going to do is going to make sure that the parameter was processed, accepted and successfully and processed by the SDHC. So once we do that, then so that's the R sub I that contains all the parameters that we got reply from the SDHC. So the first thing we do is we look for the successful parameter was transmitted and accept it. So that's when this becomes 0. So when this becomes 0, we are exactly at this point, byte 1, which is the R1 response. So we're successful there. After that, we go from that point, we go I plus 3, which we're looking parameters to be equal to 0, 1, which means that the voltage was within limit. And then we go to the fourth parameter, which would be the echo, to verify the echo was same as what we sent, which was the 0AA. So the message was, they got the message, they accept it, and then we check these two. Now, if we get to that point, then we know that the SD card states that the values within the voltage is within range and the pattern is correct. So we can say that we had a successful transmission and reply. So at this point, we can deselect the chip and we can move. We're done with command 7. So let's go to command 41. Again, command 41, the command number is 69, and we're going to send here parameter 40. Now, what the parameter 40 states is that we're going to deal with a high capacity HD. So that's what you buy in the store, what you buy today. That's the only thing you're going to get, this high capacity. So we need to put a 40 there, and then the rest are 0, and then we put just a funny checksum. And then once we send that message, then we're going to get an R1 of response. So let's look at the code. So now one of the things that this routine does is going to return the what we call the flag. And that's because, as we talked before, we're going to have a do loop between command 55, command 41, and then we check if command 41 got a 0. And if it got a 0, then we're done with the initialization. So that's what this is doing. If this is successful, that means that everything was 0, and that means the initialization was successful. So let's look at the at this code. So we wake up the SDHC here. We have our command 41 that has the parameter that we discussed. So the first step is to send the 6 parameters to the through the SPI to the SDHC, and also to the serially to the laptop. Next we go and we check, we do 8 times, we communicate with the SDHC with a dummy message to get a reply, and then we check to see if we are getting the reply, which means that all zeros. Once we get there, then we can say that we were successful, the transmission was successful, and I set the flag to be 0 because that's what we want to verify that the whole thing got initialized. This flag should be 0, and that's what we'll return. Otherwise, we'll never return the 0. So let's go to the next command. The next command is 55. This is a straightforward command. What we're going to send is the command number. Then the rest of the arguments are going to be 0, and we'll have a funny checksum, and we'll get as a reply R1. So let's look at this routine. So this is typical of what we've done before. We load the words into the array, then we transmit the array here. Next, again, we do a transmission, sending a dummy FF to get a reply from the SDHC, and once we get the reply, if it is 0, we declare success. Then in this case, we send another dummy API transmission. That makes the hardware happy, and why not? And then we deselect it. Next, we have command 58. Now, command 58, again, it's a one that we have an output of R1, and then we have 2 more replies that we have to account for. So let's see how we do that. So the first thing we do is we get the command, which is 7A, all zeros, and FF at the end. Then as usual, we just go ahead and send the command. And after sending the command, this is where things is just a little bit different. What we do is we, again, we're going to do this 8 times. So we get a response from the SPI transceiver. And what we're looking out of that response is to see whether the response is all zeros or 0, 1. And really what it means is if we get R1 all 0, that means that there were no errors as before and the command had successfully processed by the SDHC. And if we get here a bit 31 as a 1, that means that the cartridge is ready for the next step. So what I do here as a response is I say I'm going to send the command and read the reply 8 times. And during that period, I should get at least 1 response for the 0. So I say successfully, and I put the response, which would be 0, 0. And I also expect that I'm going to get a response for 0, 1, which is going to be successful 0, 1. So I'm going to do that, and then those 2 messages are going to be sent to the laptop, so I can read that both items were successful. After that, I deselect the chip, and then of course I sprinkle the new lines on and off, so the display. When I show you the output from the program, you'll see exactly what I'm doing here. So that takes care of command 58. And let's go to command 59, which is the last one that we have to do for the initialization. So this command, the command number is 7B, followed by no arguments, all 0, and then a checksum of 91. So let's look at the oh, and then the reply is just going to be an R1, which we are just going to look for the bit 7 to be 0. So let's see this. So we have the chip select within our dummy transfer. Then we have the command, the 6 bytes. This is where we send the 6 bytes. Next, we start sending dummy message. We're going to give it 8 opportunities. We're going till we get a response that when we end it with 0 hex 80, which means that bit 7 is 0. We get a 0, in which case we can say that the message had been successfully processed. Next, we do a dummy SPI transfer and we deselect the SDHC. So that what I did, I show you the flow for initializing the SDHC, and also showed you the code associated with each of the commands. So let's continue with the presentation. Okay, so next comes the sample program. So the idea here is that we learn a lot of commands, and now we're going to do a sample program that's going to exercise those commands, and we'll be building up on what we learn. So the objectives of this sample program, one is to initialize the SDHC. At the conclusion of each command, transmit to the laptop the status. So what we want to do is we want to get a status on the lab, and we can see what's going on, because later on, if we want to send something to the card and it doesn't get written, then we can go back and see what was reported to via the UART to the laptop and see what happened. So let's look at our connection. So we're going to have the laptop hooked up to our ATMEGA microcontrollers through TX and RX, PD1 and PD0. That's going to be the serial interface, the UART. And our SD card is going to be hooked up to the controller microcontrollers to the SPI interface, your clock, MISO, MOSFET, and chip select. And we'll have our card inserted. So let's look at the code. Even though we've gone through all these routines, I think it's good to see them all together in one program. So let me touch in each of the, let me touch a little bit on each routine. So here we have the initialize the SPI communication. Here we have the one that we're going to use to transfer SPI serial data between the microcontroller and the SDHC. Now what follows are the commands. We have command 0, which is exactly like what I already explained. We have followed by command 8, command 41, command 55, command 58, command 59. And here, this is where we get the routine that is going to initialize the SDHC using all the commands that we've already defined. So what we have here is what I already showed. We have to go so many cycles before we can start communicating. And here we have the, as shown before, the command 0, 8, 59, 58, 55, 41. And then we go in the while loop until we get our flag equal to 0. So let's look at the main program. But I think that's something that we really haven't looked at very closely. So first thing we do is we're going to initialize our UART. That's to transmit serial data to the laptop. Next, we initialize our SPI. Then we're going to send a message to the laptop that says our hello world. Next, we're going to go 2 lines down, and then we're going to send a message to a laptop that says init starts. That's here where we send our init card. Now, after we're done with init, the SDHC, next thing we do, it will say init done. So when we're going to look at the output, so we're going to see hello world, init starts, init done. Those are the things we have to look at. So let's go and look at the output of the program. Okay, so here we have the output. So we sent command 0, and I'm showing the command that was sent, and then followed by successful. It means that we did our check and were successful. Next we have command 8, and then we had the output, which was successful transfer, and then it shows that the voltage was within limits and the pattern was retransmitted. Next, for command 59, we do successful. Here's command 58, where we say successful for 1 and successful for 0. Each one had a meaning when we looked at the routine. Next, we said command 55 successful, 41 successful, 55 successful, and finally we send the 41 again, which was also successful, and we say init done. So we have hello world, init starts, we have all the output from the source routines, and then we have init done. So the idea here is that when you start trying to communicate with the SDHC, what you have is you can look and see whether or not the communication was successful. And that's going to be important because sometimes nothing happens and you don't know where to go. Well, you can connect your serial interface and look at these outputs. So let's continue with the with our presentation. Okay, so next what we're going to do is we're going to look at the steps needed to read a single sector. So first we'll go through the data flow that shows what commands are needed and how the microcontroller interacts with the SDHC sending commands. Then we'll define those commands as before. And in this case, we need two commands. Command 16 and 17. 16 is the one that defines the size of the block that we're going to read. And command 17 is actually the command that goes and gets the information. And then we'll go through a sample program to show how to implement this. To read one sector from the card, we need to do the following. I should say from the SDHC card. First, we have to send the command 16. That's going to define the block size, the size of the sector. Next, we have to send command 17, which says, hey, we want to read a single sector. Then we wait until we get the FE from the HCSD card, and that follows the block and then the CRC. So we have the data block plus the CRC. So let's look at the code. So start with the main. So of course we initialize the UART, the SPI. So init the SDHC, we already did that. We know how to do that. And then the new thing here is read SDHC sector. We are going to have two parameters. The sector number, that's the sector we want to read, that can be as big as 32 bits, a number that size. And we're also going to send an in buffer. That's the buffer where we want all our data to be stored. Once this routine has been executed, we're going to display the information, which is going to be in the in buffer. So let's go to read SDHC sectors. Let's go to the routine right here. So we send it the sector number, and what this routine has to do first, it has to break the sector number into 8-bit chunks. So how do we do that? So we have this defined, which is mask 234. What it does is zeros, all zeros except for the 8 last bits, which we put FF. Then we do the same, but we do for the second set of 8 bits, third, and then the least significant. So from most significant to less significant. So what we do here is we got the sector number, and we're going to take out the most 2 significant bits. So we mask it with this with mask 234, and what it does is we take out the 2 most significant 8 bits, 16 bits, and we'll do the same for the next 8, the 8 more, and then the least significant. So that's the first step, putting the sector number into 4 parameters which contain 8 bit each, which is what we can transfer via the SPI. Next, we transmit the command 16, which is going to set up the block to 512, and that'll show you that's going to be automatically, basically. And then we transmit the command 17, which is the one that's going to do all the reading, which is going to be the sector broken down into 8 bits parameters, and the in buffer where to store the stuff. Now the display sectors, what we do here is we get the in buffer, and then we send it to the laptop via the serial UINT16 routine, and we do that, and that display is going to eventually display all the data. Now I don't talk about the serial interface because something we've already done in the past. So let's look at each of the commands as before. Okay, so command 16, it has as usual our 6 bytes. Byte 1 is the command number, which is going to be command 16, but the number that we use is hex is 50. And then byte 2, 3, 4 are going to contain the arguments that are needed, and byte arguments needed for the command. So what this basically says, it says the bytes 2, 3, 4, and 5 are the ones that have the argument, and the way they have it set up here is going to request a block size. It's going to define, I should say, a block size of 512, and I'll show you how that's done here. So let's look at the routine transmit command 16. So this is the command number, which is hex 50, and let's see how we transmit the 512. So these are zeros, and then in this byte we put a 2, and then follow by 0, 0, and then this is the CRC. So 0, 2, 0, 0 in hex, 200 hex is 512 decimal. So that's how we're transmitting the block size. Now we don't have any input to the transmit command 16 because we're always going to deal with block size of 512. However, if we needed something different, then we would have to modify these routines so we can put in a different block size. So again, what we do here is we do the chip select, we send our dummy SPI transfer, which is what the hardware requires, and then we have this serial information is going for the laptop. Now we go from 0 to 6, that's going to send the 7 bytes, 6 bytes, I'm sorry, the 6 bytes to the serial laptop and also to the SPI. Now, once we've concluded this, we have a couple of things that we have to check for. So the first thing we checked is to make sure that the command was transmitted successful. And that's going to be checking the response after the transmitted command and see if it's bit 7 is 0. If that's true, then we are successful. Now there is one more item that we need to check here, and that's it deals with the transfer. So what we're going to check here is the response with in this case hex 04. That's to check for illegal commands, that would be 100. So we're going to check if we end up with an illegal command just in case. And either if we never get a 0, then we want to see if it was a legal command. Next, what we do here is we deselect the chip select. So let's go now to the next command, which is command 17, which is the one that does the reading. So what we need to provide is the sector that we want to read and a buffer to where to store the data that we're reading, so we can later on display it. So this is the command 17. We have F1, 2, 3, and 4, which I already explained how we break the sector into a 8-bit words, into 4 8-bit words. And here we have our in buffer, which is 512. This is the definition of the buffer, also for the local routine. So with chip select, send our dummy command. Then we have the command 17. Now the command 17 says the sector that we want to read. However, it doesn't say the sector size, because we already took care of that in command 16. So as usual, what we do here is we're going to send the command to the laptop and also to the SDHC, the command 17, corresponding to command 17. Next, we do a dummy read, and then we do another dummy read, and we store it in R1. And then we say, hey, is R1 not equal to FE? If it's not equal, if it's equal, then we're done. This R1 was all we needed. However, if it's not, if that we're reading is not an FE, then we have to get into this while and send more dummy commands and read the response looking for our FE. Because until we don't get our FE, we're not, the SDHC is not ready to provide the data we are requesting. So after we get out of this loop, the SDHC is ready to provide the data. So we can say that, hey, we've been successful sending the command. We got an output telling us, hey, come get the data. And here is where we get the data. We do an R1 dummy command. We get the piece of data gets stored in R1, and then we put it on the buffer. And we could actually use one line of code, but I used two just to easiest to explain. And now this local buffer, I had a local buffer for do some testing earlier. I should have gotten rid of it, but I didn't. So there we are. Anyhow, we are going to go and fill up our buffer, and then after our buffer is filled up with the 512, then the next thing we're going to do is request a checksum with these two commands. And after getting the checksum, then we're going to deselect the chip select. So anyhow, that's what it takes to read. You set the command in a nutshell. Command 16, this is how much I want to read. Command 17, go and read it. So we're ready to continue with our presentation. Okay, so next what we're going to do is go through our sample program. So we have the same interface as before, and this time what we're going to do, as usual, we have to initialize the SDHC, Next, we are going to read a single sector of 512 bytes and store the contents into an array. At the conclusion of each command, we're going to transmit the status to the laptop. And finally, we're going to display the sector in the laptop. So the idea here is we're going to put together all the different commands that I explained before. So let's look at the program. So I'm going to go fairly quick to these routines because we've already looked at this code separately. But I think it's a good idea to look at it as a unit, all put together the program. This program is going to read a sector from the SDHC. Now the communication between the microcontroller and the SDHC is through SPI. So this routine, the initialize SPI master and SPI transceiver are going to be responsible for to handle all that data that is going to go back and forth between the SDHC and the microcontroller. Now, the command transmit command 0 routine and transmit command 8, those two routines are needed for the initialization. Now transmit command 16 routine is needed for the transfer of the data between the SDHC and the microcontroller. These routines, what it does is defines the size of the sector that we want to read. So when we look at specifically at the command, we can see that the argument 02 followed by 00, that's 200, which is 200 hex, which represents 512, which is the sector that we want to read. So this routine sets up the sector. We have the command, which already explained, and then we transmit the data. There is no need for anything to input to this routine because we've already decided that we're going to use the 512 only as a sector size. Next, we have here transmit command 17. This is another routine that we need to be able to get the data from the SDHC. So the input for these routines are 4 parameters which define the sector size. So what we did is broke the sector size into 8-bit words. And next we also send to the command 17 the in buffer, which is where the data is going to be stored. So as we looked at this routine before, so this is where we send the command, then we wait for FE to be transmitted hex FC, and once that happens, then we read the data and we're done. What follows next is the transmit command 17, transmit command 41, I'm sorry. That's the one needed for initialization. So transmit command 41, transmit command 55, transmit command 58, transmit command 59 are needed for the initialization. So here we get to the routine which is going to initialize the SDHC. So what it does is first we wait for 80 clock cycles, and then we send the commands for initialization. which is 0, 8, 59, 58, 55, and 41. And then we loop sending command 55 and 41 until we get a reply from 41 equal to 0. Once we get the 0, that means that the SDHC has been initialized. Now this is the routine which reads the SDHC sector. So this routine is going to get from the main program the sector number that we want to read and the buffer where we want the data to be stored. So here we have what this routine has to do, has to take this sector number and has to parse it into 4 8-bit words so it can be transmitted. So F1 is the most significant, then we have F2 less significant till we get to the F4, which is the least significant. Then this routine transmits the command 16, which is the one that is going to set up the sector number, which is 512. And then it transmits the command 17, which gives the sector number and where you want the data to be stored. Next, we have the routine display sector. What it does, it gets the buffer and sends the data in that buffer to the laptop so we can look at it. So here we got to the main. So we have the initialize the UART because we're going to use for the serial communication to the laptop, between the microcontroller and the laptop. Then we initialize the SPI to take care of the communication between the controller and the SDHC. Then we initialize the SDHC. Next, we read the sector, which gives them the sector number and the buffer where things need to be stored. And then we display the sector. So let's look at the output from this routine. Okay, so you can see that we send command 0, 8 was successful, 59 successful, 58 successful, 55 successful, 41 successful, 55, 41 successful, that's all the initialization. And then we get to command 16, which was successful, which sets up the size of the routine. And finally, we send 17, and here we can see the output of our sector. Should be 512. And so that kind of gives you the idea of the output and how everything is working. So how this works. So we can go back and continue with our presentation. Okay, so now let's move on to the reading multiple sectors. So we're going to start as usual by presenting the data flow to read multiple sectors. Then we're going to define the commands. To read multiple sectors, we're going to add 3 new commands, which are going to be command 12, which stops the transfer of data, command 16, which we already know, this is not a new command, which is defines the size of the sector, and command 18, which does the multiple reads. So basically we select the size of the sector, we start the reading multiple sectors, and then we stop it with command 12. And then we'll go through a example program. So let's get started with the flow of the data flow. To read multiple sectors, we have to follow this flow. First, we need to then send the command 16, which defines the size of the block. Next, we have to send command 18, which is going to do the reading. Once we send command 18, we wait for the SDHC to send the message FE, which it means that it's ready to send data, and we go and get the data. Next, we do the same, wait again for FE, and then we get the data. And when we're done getting all the data, we send the command 12, which says stop the transmission. We are basically done. So let's look at the actual code. So this is the routine that's going to do the work, which is read SDHC multiple. So what we do is we need to provide the sector number where they need to start reading, or I'd say the sector that we need to read first, and then the number of sectors we have to read from that point on. So to define the sector where the reading starts, we have, as usual, we use the sector number is parsed into 8-word 8-bit word, and from the most significant to the least significant. So once we do our parsing, next thing we do is we transmit the command 16, which is going to define the size of the block that is going to be transferred, followed by the transmit command 18, which is the one that actually is going to do the data transfer, and command 18 needs the sector where to start and the number of sectors to follow. And finally, we send the command 12. The command 12 is the one that stops the transmission. So let's look at the main program. So we have sector number, which we define our sector to read, our first sector to read, I should say. And then we say after that I want one more sector to be read. So I need this one plus one more. That makes it 2 sectors. Next, I have a init UART, init SPI. What it does is initialize our transfer with the laptop, which is serial UART, and then the init SPI enables the transfer of data between the microcontroller and the SDHC. Next, of course, we have to initialize our SDHC. And finally, what we do here is we read the SDHC multiple, which we provide the sector number and the number of sectors. So let's look at each of these 2D routines, number 12 and number 18. So let's start by looking at number 12. So number 12, to send the command, we have to send the command number is going to be 4C, hex 4C. Then we send all zeros for those bits for the arguments, and then we send a 01 as a dummy checksum. So let's look at the routine. So what we do here is we send the command 4C and all 0 and a dummy checksum. This comment is incorrect. So next we do the chip select, and we send the command. Those are the 6 bytes. So we send it to the serially so we can display it on the laptop, and we send it to the SDHC. Once we've done that, then we get into a loop, sending dummy message to the SDHC to get a reply, and we keep see if during 6 times we get the reply, which is the whole message 0. That means that the message was accepted and was successful. And that's what we provide here. So this message, by the way, you know, I think I already mentioned, is going to stop the multiple block read or write. Next, we have our message 18. The message 18, we're going to have byte 1, of course, is the command. I should say command 18, I'm sorry. So the first byte is going to be the command number, which is hex 52. And then the rest of the bytes, I should say byte 2, 3, 4, and 5 are going to contain the sector number where we want to start our reading, and byte 6 is going to have the checksum, which is a funny, it's a funny number because we've disabled the checksum, but we have to put something there, so we put a 0, 1. So let's look at command 18. So what we do is we have a routine which is going to take F1, 2, 3, and 4, which is the sector number that has been parsed into 8-bit words. And then we have, which is the initial sector number, and then the number of sectors we want to go through. So here we have the command 18, the array that has the command itself. And these loops, we send the SIG parameters to the serial interface, so we can see in the laptop, and also to the SDHC via the SPI. Now, once we send the message, the command message, the next thing we do is we're going to get into this loop. This is the first loop is going to say how many sectors we want to go and we want to read, and then we're going to have an internal loop which reach each of the sectors. So this is how we start. So the first thing we do is we send dummy message to the SPI transceiver to get a reply, and we continue to do that until we get the reply FE. FE means that they're ready. The SDHC is ready to send data. Next we go and we get the data. In this case, what I'm doing is with this statement, I get the data, and next I display it directly into the serial. I'm not saving it into a buffer because it's just too much additional code, and all it does is create confusion. And you can certainly do that based on what I did for the single read. So what I do here is I get the first block, and then I display it as we go on the laptop. Next, I go and get the do this again, and I'm going to do this as many times as required by number of sectors to be read. So we do that, and once we're done with this message, we sent another dummy message to the SDHC, and next we send to the laptop. We report that the reading was successful, and then we deselect the chip select. So those are the two messages for the multiple block read, multiple sectors. We have two different commands, the 18 and the 12. The rest is same as before. So let's continue with our presentation. Okay, so let's look at the example program where we go and get two sectors. So first, as usual, we initialize the SDHC. We're going to read two sectors of 512 bytes. At the conclusion of each command, we're going to transmit the status to the laptop. And finally, we're going to display the two sectors. The schematic is same as before. We are going to wire the serial lead to the laptop, UART transmission, and then we're going to do SPI transmission with the SD card. So let's look at the code. The purpose of this program is to read multiple sectors from the SDHC. Now, most of these routines we've already looked at, and so I'm going to go fairly quick. Now, the only two routines that we're introducing here are the command 12 and command 18. Command 12 is to stop the transfer of data between the SDHC, and command 18 is to start the transfer. So let's start going through the routines. So we have the init SPI and SPI transceiver. Those are required to read for data to be transferred between the microcontroller and SDHC. Next we have command 0, command 8. Those two are used for the initialization, which we already discussed. Then we have command 16, which defines the block size, which is 512, which we've already looked at. Next we have here command 17, which was used for the single read, and we have command 41, and then I should say command 41, 55, 58, those are required for the initialization. Command 59 again is required for initialization. Now command 12 is the one that we looked at, and is the one that we're going to use to stop the data transfer. And we have here what it looks like is basically command number is for C hex, and all the rest are 0. We transmit information, then wait for the reply to be all 0. We declare that the command was accepted and was successful. Next we have our command 18. That's the one that we're going to use to transfer multiple sectors. So here we have the 4 parameters, which are the sector where we start that has been parsed into 4 8-bit words, and then we have the number of sectors that we want to transfer, starting from the sector defined by F1, 2, 3, and 4. So we have the chip select, and then here we have the command. We transmit the command to the serial interface, to the laptop, and also to the SDHC. Next, we have 2 loops, one which is going to get the how many sectors we need to get, and the other one that is going to get each of the sectors, the data on each of the sectors. So we wait for FE, for the SDHC to reply with FC hex to our transmission. Once we get the FE, that means that the SDHC is ready to transfer the data. So we go and get the first 5 12 words, and then once we are done with that, then we go back to the loop and get the next sector. Once we are done with getting all the sectors required by the number of sectors, then we make one more dummy transmission to get and then we declare success because we already got the data. Now in this case, what I'm doing is every time I get data, I go ahead and display it directly into the laptop, so I don't have to be transferring buffers, because then the whole thing gets just too complicated, too many, not complicated, but too many lines of code, and gets very hard to explain, but you folks already saw how I did it for the single transfer. So you do the same thing here. Here I just took a shortcut and displayed directly into the laptop. Next, we have the init our SDHC. Basically, we wait so many cycles required by the hardware, and then we send the command 0, 8, 59, 58, 55, 41, and then we get into a loop sending the command 55 and 41 till we get the reply from command 41 equal to 0, and that tells us basically that the SDHC has been initialized. Next we have here, this is the one that read the sectors. Next we have the one that reads the multiple sectors. For the multiple sectors, what we do is we get the sector number where we want to start, and we parse that number into 4 8-bit words, which are the ones that we're going to send to the SDHC when we request which command 18, which is going to be the sector number, and then it's going to be followed up by the number of sectors we want to read. So we get from the main program sector number where to start and how many sectors to go from there. So once we've parsed our sector numbers into 8-bit parameters, the most significant to least significant, we send the command 16. The command 16 is going to define the size of our sector, which is 512. It's the same we've been looking at before. Next, we're going to transmit command 18, which has sector where to start and number of sectors to read. And then once we're doing with all our reading, we're going to send the command 12, which makes the SDHC stop all transmission. It basically informs the SDHC that we had all the data we need to stop. So here we got into the main. In the main, we're going to define the sector number where to start. And here we have, hey, from this read to sector, so read sector 8192 and sector 8193 basically. Then we initialize as before our UART and our SPI to enable communication with the laptop and with the SDHC. Next we initialize our SDHC, and finally we send the multiple sectors. So let's look at the output. Okay, so what we have here is a statement that says the command 0, 8, 59, 58, 55, 41, 55, and then we had to do another 55, 41 were successful. This is where we are doing our loop waiting for the 0. So eventually we get 41 equal to 0, and we say we are successful. Once we are successful, we send the next command is command 16, which defines the size of our sectors. And next we send this the command 18, which is the one that actually goes and gets the data. And here we have the first sector, and here we have the second sector. There was nothing in those sectors, so they are all 0. But anyhow, this shows you that actually we read 2 sectors. Then after doing all the reading on command 18, we sent the 18 successful, which means that we were able to get all our data. And finally, we do command 12, which is, hey, stop sending us data, and that was also successful, and the data was stopped. So with this, we can continue with our presentation. Okay, so let's look at the next subject, which is, by the way, the last one. So what we're going to do is we're going to write to a single sector. So first item is going to be, we're going to go through the data flow. followed by the definition of command 24, which is the only command new command that we're going to need for this, for the writing the sectors. And then we'll go through a sample program. So let's get going. This flow shows what we need to do to write a single sector to the SDHC. So what we need to do is, first we need to fill up what I call an out buffer, which is going to contain all the data that we want to write on the SDHC. Because we're going to do a transfer of a whole sectors at the time. So we prepare a out buffer with all the data that is going to go in the sector. Next, we have to define in what sector we want to write. Then with those two pieces of information, then we can call command 24, which is responsible for writing the block. And then after writing the block, what we do is we wait until the bus is it's idle again, which is going to show as 0FF. So let's look at the program here. So we have a routine that says write SDHC sector. So the information that we're going to provide to that particular routine is the sector number where we want our data to be stored, and then the buffer that contains the data to be stored. And with that information, we're going to call the command 24, which is the one that's going to do the storing. So as before, what we do is we take the sector number, we parse it into 4 8-bit words, with the least significant portion on F4, the most significant portion on F1. And we call the routine that's going to do the storing or writing to the sector, which is command 24. So we have the sector plus the out buffer, which contains the data is going to have to be stored. Now, one of the things that we're going to do is we're going to write, and then we're going to read to verify that whatever we wanted to be written got actually written. So in this case, the display sector, which we've seen before, it basically we read a buffer that we just wrote, and we display it to validate that everything got written. So let's look at the main program. So I define a couple of an in buffer and out buffer. It's a buffer that we're going to use to store the data that we're going to write, and then we have the buffer that we're going to get the data from the SDHC to validate that it's correct. I have any sector, ISI sector 18. So what I do here first is I initialize the UART and the SPI, which are going to enable us to talk to the laptop and to the SDHC. Next, we initialize the SDHC as usual. Then we have this routine that is called a pattern. So I needed to write something into the sector. So I decided I'm going to do a routine that when I write a 1, it puts into the out buffer a pattern that in this case is going to be all hex A. And then if I put I call the same routine pattern, but have the values pattern is 2, it's going to write all B's. So what I do here is first I fill up a buffer, the out buffer with a pattern which is going to be equal to 1, which is going to place all hex A in the 512 positions. Next, I write the sector, by giving it a sector number and the out buffer. Next, I read that same sector that I just wrote to verify that all the values are hex 5, and then I display the buffer. Next, what I do is I have this pattern 2, and I fill up the out buffer with pattern 2, which is basically going to place hex B in all the 512 locations. After that, I go ahead and go to the same sector number, which is 18, and write the out buffer, then which are all going to be B. So I had A's first, and I'm going to be, with this command, I'm going to be overriding with B's. And then I read the sector and display it. And so basically I should have first the 512 sector that shows all A's, and then the same sector, but in this case it shows all B's. So let's look at the routine that does that, which would be the command 24. So we have command 24. So what we're going to do is we send the command number is 58. I have it here. So it's going to be command number 58, and it's going to be followed by the argument F1, F2, F3, and F4, and then I'm also going to provide an out buffer, which is where we're going to store all the data. That contains the data we're going to write. Sorry. So we select the chip SDHC. Then we send this SPI dummy message because it's what makes things work smooth. Then we send the command 24, which is going to be the 58, then the locations of the sector that we want to write, and then a dummy checksum. So at this point, what we do is we send the 6 commands, and after we send the 6 command, then we're going to go 8 times waiting for evaluating the response. As soon as the response is 0, which would be the bit 7, hex 8 is 0, then meaning that the bit 7 is 0, then we're going to declare that command 24 was successful. We're going to transmit that to the laptop. Next, what we're going to do is we're going to also evaluate if the next message after the 0 it's not 0, then we're going to call a command to be illegal, and we're going to stop what we're doing. After that, what we do is we send another dummy message, and then at this point what we're going to start doing is waiting for the SDHC to send us the FE command. I'm sorry, I should say that I'm going to send to the SDHC the FE command, which is going to tell it that I'm going to start the transmission. Before, when we used to get the FE, meant that we were going to get we could go and get the data. In this case, it's the opposite, I'm sorry, where we send the FE and tell them, hey, we're going to send the data. After that, what we do is we start sending the 512, the data, the whole buffer, from 0 to 512, 511 actually. And then we send a couple of dummy checksum. After that, what we do is we send a dummy message so we get a response. So what we're trying to do at this point is verify that the data got across and got stored. So to do that, what we do is we send the dummy message, store the value in the response, and then check to see if the response ended with 1F is not equal to 5. Next, if the if this is true, then the write command was not successful, and we write error. And now, if this is true, then the next thing we do is we want to wait for the bus to be idle. So what we do is we go in this while, and we'll do it as long as the output from the SDHC is not FF. Once it's FF, then we know that the bus is idle and everything got accomplished. Next, we unselect the chip, and that's what it takes to transmit the data. So let's continue with the presentation. Okay, so now we're going to go to the sample program, which is the last one, and we're done. So first we're going to initialize our SDHC. Next, we're going to load the buffer with 512 bytes. It's going to be loaded with a pattern of all hex AA. Next, we're going to write the output buffer to the SD card. Once we've written to the SD card, the next thing we're going to do is we're going to read the sector to verify that whatever we wrote, it got written. Next, we're going to put a different buffer, a different pattern into our output. And we're going to write it into the SD card. And so the idea here is we write the pattern of all hex AA, and then we write the pattern of all BB. So we show that we write A, we display it, then we write B, then we show that the AA got overwritten by the BBs by the display in the output. So at the conclusion of each command, of course, we're going to display the status. And then we're going to display the sectors, the A's, and then we're going to display the B's, which is written the same sector. So let's look at the code that is going to accomplish this. This program is going to write into a sectors on the SDHC. All of this code we've already explained and looked at it, but I think it's important to look at the whole program at least once together. So we have the initialize the SPI and SPI transceiver. Those two routines are going to be responsible for the communication between the processor and the SDHC, which is SPI. Then here we have send command 0, command 8. Those two are needed for the initialization. Then here we have transmit command 16, which we are going to need to set the sector size, which is going to be 200 hex, which is 512. Next we have command 17, which we use to read the sector, followed by command 24. That command 24 is the one that we're going to use to write the data. So I'm just going to go a little bit more of details in this particular command. So the input to this routine is going to be F1, F2, F3, and F4, which is the sector number, followed by the output buffer that contains the data. It's going to have to be stored. It's going to be stored on the SDHC. Now, so what we do here, we do the chip select as usual. We send the command, which is the sectors plus a dummy checksum. Then once we send the command here, we verify that the command got across successful or not. In either case, so we're going to report it to the laptop. So the first portion is to verify that the command got through. And the next thing we're going to do, we're going to have to verify that the data actually got through and stored. So after sending the, once we have successful, then we send the FE command, which what it's going to do is tell the SDHC that here goes the data, the 512 block. So this is where we just go around and SPA transceiver, we just send item word by word of the buffer. Then we do a couple of transmit dummies, which are dummy checksums. And after doing that, the next thing we do is we grab and the next command, we send the dummy and the reply, we put in response. And now with this reply, we're going to verify whether or not the data got transferred and what got stored correctly. So what we compare is the response with the 1F, which is basically 11111. And if the response is 5, which would be 0101, then that means that the data got transferred and stored correctly. If we don't get that value, that means that there was an error. So once we know that we were successful, then what we need to do is wait until the bus goes idle. And we'll know so this is this while, and we know that the bus goes idle when the reply from the SDHC is FF. So after waiting, once the bus is idle, we're pretty much done. Next comes command 41. That command again is needed for the initialization. Next, command 55, command 58 are also needed for initialization. 59 is also needed for initialization. So finally, we get to this. They need SDHC. That's the routine that's going to initialize our SDHC as usual. So we wait our 8 clock cycle, and when we send command 08, 59, 58, 55, and 41. And after doing that, then we go in cycle here till sending command 55 and 41 until we get a reply from command 41 that is 0, which means that the SDHC has been initialized. Next, we have here read the sector. We've already looked at this, which is command. We have a read sector. Sorry. So we put in we said command 16, which decides the size of the block, and then command 17 actually gets the location and then reads the buffer and places it into the in buffer. Now here what we have is the routine that I was talking about, the pattern. So we're going to have, if we get a pattern 1, then we're going to fill up the whole buffer with all A's. If we have a pattern number 2, then we fill it with all B's. The idea is that we're going to first send out, we're going to write the buffer of all A's, and then we're going to read it and verify that they are all A's. Then we're going to send all B's, which are going to rewrite the A's and then read them back to make sure everything got rewritten. So that's the kind of the idea of this pattern. Now the right sector, what the input to this routine is going to be the sector number and the output buffer. So what we do is we take the sector number and we break it into 4 8-bit words from the most significant to the least significant. And then we call command 24, which these 4 F1 through F4 defines the sector which is going to have to be stored. And then we have the output buffer where that contains the data that's going to be stored on the SDHC. Display sector, that's the one that when we read something from the SDHC, we are going to display it on the buffer, and that's what we're going to do now. So let's look at the main program. So we have the sector number is 18, and then we're going to initialize our UART, which is going to allow us to talk serially with the laptop. We initialize the SPI, which is going to allow us to talk serially with the SDHC, so the SPI protocol. Then we need the SDHC. So first we set pattern to 1, and then we call pattern, which is going to fill up the buffer with all 1, which was all A's. Next we write all A's into this sector, which is sector 18. We write the out buffer, that should be all A's. Then we read the buffer, and then we display the buffer to verify that they are all A's. Then we set parent to 2, fill up the out buffer with parent equal to B's. Then we write all B's, we read all B's, and then we verify that everything that written was all B's. So let's look at the output of the program. We have all A's, and here we have all B's. Sorry. We have all A's, and we have all B's. Now let me stop here for a minute. So what we did here is we send the command 0, command 8, command 59, command 58, command 55. That's the initialization, and then we went 41, that was not successful, so and sent 55 again, which was successful, and then we sent 41, and eventually got 41 to was successful. So next we went and sent command 24 to write the all A's, and after we did that, we wait for the bus to go idle, and then we send the command 16 and 17, which are successful here, to read and display the data. And what we have here, the whole sectors, all A's. So let me continue here. So after we wrote all A's, so then we have command 24 successful. Next, we did the same operation, and this time we had command 16 and 17 again to display the data, which are at this point all B's. So basically what I've done here is I showed how I could read all A's to the to sector 18, and then display what was on sector 18, then write something different, which is all B's, and show that that was also done successful because it overwritten the A's. So let's that concludes this program, and let's continue with our presentation. Okay, so what comes next is the summary. So today I give you a description of the SDHC. Next, we went through the data sheet, hitting some of the highlights. Then we talked about the card functionality. In sample programs, we learned how to initialize the card, then how to read a single sector, how to read multiple sectors, and how to write into one sector. And here we are at the summary, and I would like to thank you for spending all this time with me, and I hope you've enjoyed it. Thank you very much.